All right, so I think I've had one of you before, right? So I like whiteboards, and I like doing things. So I will try my hardest not to kill you with PowerPoint, though there will be some things that might just be better explained with PowerPoint. But I'll try to, like, one, I have to record these things anyway. But two, I'll try to get PowerPoints or something like that to put up on Blackboard after class, just so that all the important information is there. So this is computer communications, and it is basically the fundamentals of networking. So if you have right, we've all learned this in various computer science courses, right? We have a client-server model, right? And the clients go to this cloud thing and talk to the server. This class is, what the hell is that? Okay? There's a lot that actually goes on in here. And we will spend this entire semester discovering what's inside of here. But in order to do that, we'll have to talk a little bit about, because we have a programming assignment, and I'm not going to make you make like a router, right? So we're gonna have to talk a little bit about doing sockets on the client server side. But you will actually program a socket, and we'll introduce errors in that network stream, and you'll have to correct for them, right? And so that's where the C programming comes in. Anyway, so what this class is not, this is not an IT class. We're not going to go in and say, hey, this is Cisco iOS, and this is Brocade, this is how you run a Brocade switch or whatever, right? You can all go and do that, and I've done that, and it is terribly boring. This is actually how to build something in that so that you can, you know, be the guy that is the smart guy underneath, and then you pay developers to build the human interface, right? So, if you think of networking, networking could be described as something higher function, right? There's distributed systems, right? It can also be lower, like the electrical engineering guys, right? This is signaling. And then where we are, or you can call this communications too. Where we are is networks. What do you think distinguishes these three things? What's a distributed system?
Information systems.
Yeah, they're information systems. Distributed systems is what technical people call the cloud, right? It is a network of computers accomplishing tasks, and they're using a network to communicate back and forth, right? For the electrical engineer is, how do we send signals across a wire or through the air and have those signals reliable? Right? There's a lot of stuff that goes into that. We will touch a little on both of those. But we're going to say here, this is the cloud part, right? Networks. And when we talk about networks, what we're really talking about is packets. How do packets move from one place to the other? There are other types of networks that are not packet switching networks. Any examples?
InfiniBand?
Huh? InfiniBand is a packet switching network.
Is it?
Yes. No, think more old school.
Transport layer.
Nope, more old school.
Like old telephony.
Huh? Telephony, right. Right, remember, you know, like if you ever seen like you get stuck watching the History Channel for whatever reason, right? And they have these big giant switch networks where people are taking wires and sticking them in, right? Before you dialed the phone, you would call an operator and say, hey, I want to call this person. If that person was in your local area, you could just call them directly. If they were out of your local area, and when I say local area, I mean like Colorado Springs would be more than one local area. If they were out of your local area, you would have to call the operator and have them connect. And the reason you had to call, go ahead.
Sorry, what is it called again? The name of the switch that you just mentioned?
Oh, so this is a switched network, like a fully switched network.
Example.
Oh, telephony, telephones,
All
right.
right, thank you.
So you would call the operator, and the operator would actually connect you. And when they did that, it was because the networks, right? If you wanted to call here, this is your local area, right? And you wanted to call over here, right? There was a switching place with people in it, right? And you would call the operator, and they would literally take a wire and stick it in another hole so you could call this person. They would physically move it. And if you wanted to call long distance, right, then you would have to, they would connect you over here to an international switching station, right? And they would connect you to here, somebody else would connect you overseas, right? These were choke points. This is why they could extort you for money for long distance, right? Because it was very expensive because you had to run all the wires. A wire can only take one communication at a time. So and that's the main difference between switched networks and what we're going to spend most of our time on, which is multiplexing networks, right? How do you share communications across the same wire with multiple entities? So a brief history. When did packet switching networks actually come about? Anybody know where, when?
DARPA.
Huh?
DARPA.
DARPA. It was called ARPA at the time, right? Thus ARPANET. It was later named DARPA, and that's the Defense Advanced Research Project Agency, right? What time?
1961, 65?
So the project started in like 1966, 67. It came online in 68. In the 70s, people were actually using it. And the internet consisted of, you want to take a great guess on how many nodes?
4.
Five. Four is really close. There was 5 nodes in 1970, right? There was one at UCLA, one at UC Santa Barbara, one at Utah.
Stanford or Berkeley?
It was Stanford Research Institute, SRI, and it wasn't Berkeley, surprisingly. Utah, right? So 5 networks for the whole internet, but it started expanding, right? And so by 1975 or so, there was the National Science Foundation had taken over. Really, they created their own internet, their own ARPANET at the time. And it was much bigger, and there was much more universities participating. Then they joined those, right? And it just kept growing and growing. In general, it doubles every 18 months, just like Moore's Law. So today, nobody actually knows how many things are connected to the internet. There's no way to measure it. That's how many there is. But we know it's growing, and we know it's growing because we can do sampling and kind of estimate. Go ahead.
Is there any gross estimate on the number of devices connected?
So to give you an idea, in 1995, I think they actually mapped out most of the internet, and it was like 25 million connections. In 2005, they took a sampling and projected it out, and it's like a billion connections. And it's growing, and it's likely to grow even faster in the future than it is now. Anybody want to take a guess why?
What's the IoT?
IoT, Internet of Things, because your refrigerators can be connected to the internet. Right. Right. So everything is, not only is your refrigerator going to be connected to the internet, but every car is also going to be connected to the internet. Right. Every mode of transportation, everything, and from just locating devices or locating objects, like your backpack might be connected to the internet. Right. So it's liable to jump from the billions to hundreds of billions, if not trillions, of devices, all connected to the internet, doing something, providing data. Why do you think that we're gonna stick in networks and discover how this works? Any guess why are we sticking there? Honestly, in your jobs, it might be more useful to get like internet architecture, go do a Cisco iOS course, right? Why do we stick here?
Routing.
Huh?
Routing.
Well, routing is part of that Cisco iOS. Go ahead.
Because it's really important to understand how machines communicate with each other.
Correct. So if we stick down in the fundamentals, this gives us an opportunity to make the network better. The internet is evolving. It is changing all the time. The internet of today is not what it was 10 years ago. Anybody sit down and contemplate that 10 years ago, like Facebook and Twitter and none of that actually existed? Right? Amazon? Right? Things that seem like a bedrock principle of the internet. 20 years ago, Google wasn't around. Or if they were, it was really, nobody was using it. It was only the nerd search engine. Right? It's about that 20 years, right? So the internet is transforming, and what we use the internet for is also transforming. So it used to be that we used internet to resource share. The internet was designed for resource sharing. So go ahead.
Real quick, Amazon was founded in 1994.
Oh,
So 23 years ago.
23 years ago.
Destroyed it.
When did actually somebody make a purchase on Amazon? That's the real question.
Yeah. Being a
So,
library.
I found in my dissertation in 2010 also. Actually, I actually literally started it in 2010. The idea had been incubating since 2004, maybe. Right? So there's a beginning and then there's an actual usefulness. But
Brick and mortar.
go ahead.
For this question, you were saying internet is designed for something.
Is for resource sharing. When the internet was designed, ARPANET was put up, it was for resource sharing. Right? You are University of California, Santa Barbara, and you have this big mainframe computer, and I'm Utah, right? And Utah's like, hey man, I have a really big need for this to run some computer cycles, right? Can I borrow your computer? Well, it used to be you had to jump on an airplane or a bus, right? And drive over there and do it and come back. And so the idea was like, hey, can we build this network with this new fangled technology of over-the-wire communications, and can I use your computer? Right? Locally, it was for like, can I use your printer? So not every computer needed a printer. And then, of course, they built this thing, and what did it get used for? They used it for those things too. What was the first big app of the internet? Killer app.
Doom?
Made everything expand.
I just remember Doom.
No, it's way earlier than that. Way earlier than that.
Message boards?
Nope.
That's what we use the computer lab for.
Email.
Of course.
Email was the first killer app of the internet, right? So, if you want to steal CPU cycles on UC Santa Barbara and get results back, you probably want them to be correct, right? So one of the main problems in networking is, that's not going to work, reliability. Very unlike this piece of paper. So you want to send a communication across a wire, right? So let's just start talking about wires because wireless becomes really complicated. But we're going to deal with that. Look forward to the future, right? So you want to send a communication across a wire. How do you do that?
Handshake.
Well, that's higher. Like let's talk
Voltage.
like old school, like Morse code saying
Voltage.
communication across a wire.
Voltage, yeah. 10.
Yeah, you can modulate voltage, you can modulate frequency, right? There's just a number of things you can do. The problem is when you get very far away, what you sent isn't always exactly how it arrives, right? Because you try to make these wires and you try to twist them at very even intervals, right? But there is some variation, and so the more stuff you try to stick in this wire, the more often the signal fails at the other end. Right, so that actually introduces a reliability problem. And one of the main things that you have to tackle when dealing with network is reliability. Because it's very easy for me to sit here and talk to you in class. I could write up on the whiteboard, right, and you can read that. And you know, the guys are back, maybe they needed glasses or something and they can't see, right? But it's fairly straightforward, right? If I want to talk to somebody across the courtyard, right, I have to get a megaphone or something to project my voice, right? But the more I do that and the further they get away, the less reliable it becomes, and eventually the messages will be garbled. So you can introduce all sorts of algorithms and technologies on top of that to correct for mistakes or detect mistakes. Really, that's our two options. We can correct or we can detect. The problem is every time you add something on top of that, that can fail also. Right? And so you keep every time you make something more complicated, just like security, so there's one bug for every 1,000 lines of code. Right, so in security, if you add 2,000 lines of code to try to secure your system, all you've done is introduce 2 more bugs. Right, so there's a chicken and the egg problem. The more complicated you make the system, the more unreliable it becomes. So how do you make things more reliable without making it more complicated? And the answer is you need to be clever. Right? You try to do this in very clever, small ways that are well understood.
So why wouldn't we just fix this comm signal layer and not worry about adding another layer on top of it?
So we do fix the comm signal layer, and we do that incrementally. So if we talk about original Ethernet, right? There's various standards from was really, really slow. I don't even know what the original Ethernet was, but it was terribly slow. Things that would be completely unacceptable today, right? And then it goes to 1 meg, and then 10 meg, and then 100 meg, and then gig. And then at the enterprise level, you have 4, 10, and 100 gig, right? So those comm layers actually do change. And they change because silicon becomes faster, and people are more discover. People decide they want to go get their PhD and out of some kind of inner hatred for themselves, and they go get their PhD, and they're like, "Hey, I have this really neat idea," and I write a paper about it, and then somebody else goes and monetizes it. Right? That's how it works.
I'm the better.
I was lucky enough for somebody that paid for mine at least. So those do change, right? And we know that they change. We use them all the time. So and it's pretty transparent to us, right? So you go to Amazon and you buy a switch, and it's a 100 gig switch because you didn't read the details, right? It interplays with your gigabit switch, right? So all those things are, and we'll talk about the thing that's really hard to change here in a minute, but the lower layers are pretty easy to change. The upper layers are pretty easy to change. And we're going to talk about that. I'll draw it up here, right? So this is the physical right here. This is what you talked about, right? Why don't we keep updating this? And this is, we'll just call this apps for right now. And we're going to fill in the middle. And we're going to figure out what's right here. All right, so we talked about the switching networks, right, where people were switching things, right? After that, then they had a computer switch things, but it was still switching things, right? Think of it as like a relay, right? A computer would flip a switch and it would literally like move things around, right, physically, and the communications would happen, right? And then somebody came up with a bright idea. When computers were coming, they're very different than telephones. So when we're talking over telephone, the line needs to be dedicated, or at least it used to think it needed to be dedicated, right? Because the communication is very constant, right? And then if you call mom for Mother's Day, and then the next time you call her is like her birthday, right? So there's this long, long time between, right? And so in reality, most of the telephone lines at the endpoints they're being used, but the nodes are not always connected, right? So it kind of works. Internet does not work that way. Networking doesn't work that way, right? Just going to www.google.com starts a number of processes, right? Some of which don't involve Google or you, right? First of all, you need DNS, right? It's what keeps the internet sane, right? So I go to www.google.com and it gives me an IP address, maybe some alternate IP addresses, and it comes back to my computer, and my computer says, okay, I'll go here, right? So it's a very bursty and spontaneous action that goes to multiple nodes. So that's different than a telephone communication line, right? The internet networking is very bursty. And the way that it works in networking, not just the internet, but all networking, is that it's often multiple computers are involved to figure out some problem, like name resolution, and then it shoots off to get the information, right? And then you get the information, and then you read, and it's not doing anything again, right? When you're on like news.google.com and you clicked on an article and it takes you to the Washington Post or whatever, and you're reading it, right? There, other than the ads that keep flashing at you, right? You're not actually querying Washington Post. You already have the data, right? And you're reading it, right? So that's different. So let's design a network. We're going to go to news.google.com. This is Google. What's our favorite news site? It's a trick question. There are none. Right? So we'll just say WAPO, right? So we want to communicate, right? But we're not the only ones that are communicating. Some old school guy is down here using Yahoo, right? And then some people are getting all their real news from Facebook. And this is that big mysterious cloud, right? So we connect into here, and things come out of here, right? But for right now, let's consider that this cloud, all the incorporation has happened, and you know, Comcast now owns the entire infrastructure of the internet, right? They have bought all the other companies, so it's just Comcast, right? So we'll just call this ISP. And so let's say the ISP, because they're Comcast and they're trying to be cheap, right? It has 100 megabit per second connection, right? To move data from one place to the other. The question is, how many clients can you have on this side?
As many as you want.
Well, Comcast
Until it
thinks so
reaches
for
100
sure.
meg.
But like, so we want to make the internet better,
Right.
right? So let's just walk through, right? The obvious, simple, naive answer is, if we want to give these guys 5 megabits per second, how many do we give? Naive answer. 20, right? Because we take, you know, this divided by 5 equals 20, right? But I just told you the internet was bursty, right? So it's very unlikely all 20 of these people are going to say, ooh, I got to get my Google Newsfeed today. And the one guy that's going to Facebook. Oh wait, there's 19 guys going to Facebook, and the other one guy's going, right? So it's very bursty. Let's say these guys are super active users, right? And they are actually using their net, and we're doing this because math is better if it's simple, right? With good, easy numbers, right? This is a totally unrealistic number, right? Let's say that each of them are using their connection 50% of the time, which basically means they're streaming movies and sleeping to them, right? So they're 50% of the time. Now, how do we utilize this network we can over provision the network, right? Because some of these guys will not be using it, and some of them will be using it. So we can over provision. We can add more people, and probably still stay under 100. Right? At 50 is going to be a pretty small number. So this is why I told everybody that you need a probability. So if each of these are clients are using 50%, what is the odds that all of them are using it at the same time? Real number, not figuratively.
Like 1/2 to the power of however many people that are.
Yeah, one half to the power of 20, right? Which is what?
Small.
It's really small. We have about 1 in a million, right? Chance, right? And then we could calculate, hell, how many is it? 19, right? We could calculate all that. We could do a distribution, right? A binomial probability. So what is 30? If we do 30, right? Now there's a chance that all 30 people will get on. What's the chance that all 30 people get on?
1/2 to the 30.
Right? 1/2 to 30, right? It's really low that all 30 will get on. All right? This is why your cable modem, because the cable modem is a shared resource, right? So this is why your cable modem degrades in the afternoons, because they over provision. Now, it's not that you don't serve those guys, you just serve them at a lower speed.
People's internet goes slow at 4 p.m.
It's around 6. It's about after the time you get home and you decide that Netflix is on your agenda.
So I just wanted to know, because of where I work, because they only tell me it's line signals that cause internet.
No, this is the reason.
Well,
They over provision your network.
Over provision.
Yep.
Is there any other reasons? Or
I mean, there's all sorts of other reasons, but the most obvious answer is it's over provisioning. It's the same reason airlines do this also. Airlines know that people, like 8% of people, and I don't know where these 8% of people are because I have never not shown up to a flight I paid for. Right? But 8% of people book an airline ticket and then don't show up. Right? So they overbook. And occasionally, those guys show up all at the same time. And then, you know, they're saying, oh, we need somebody to take a flight, we'll give you a voucher. And, right? And not pay for your...
And they're dragging people off planes.
They're dragging people off the planes and, yeah, so.
Professor, is this the same with like the LTE network, like with our phones? Sometimes during certain times?
Yes, and it's, when we talk about wireless, it's way worse than you think. Anybody actually go see the eclipse besides me? Okay, did you try to text or anything at all during that time?
There was no service.
Oh, but your phone said you had service.
Yeah.
It just didn't work.
It's like going to a sports stadium or something.
Yes,
Overload
right?
the network.
Yeah, try to get a text out after that somebody just scores a last minute touchdown for the Super Bowl, right? You can't get a text out in the whole city. And we'll talk about wireless is actually exponentially worse than a wired. So we'll talk about that. So you can do 30, right? So what is the 50? What is the most probable if you do 30 and it's a half, right? What's the most probable number that the number of people using the network at the same time? 15, right? Because it's literally half of 30. This is why I use easy numbers, right? That way I don't have to go here and like and somebody be back like, oh, that's wrong. Right? So, yeah, so we do over provisioning, right? So the other way that we can do it is we can take advantage of the structure of the internet. We're just going to call these clients, right? Because what's the difference between a client and a server?
Resources.
The server is maintained by somebody else, right? Kind of like your parents' computer. So the structure of the internet is right. You don't talk very rarely do you talk directly to the thing that you want to talk to. right? Right, even if it's not Intel's. So this node communicates to this, and they do it in a way that it seems like they're directly communicating, but we know they're not, right? Because this is the cloud. This is that magic thing that we're studying. Right, so for content delivery, you are Amazon Prime and you're gonna start up a video service or Netflix or some other of the big content delivery, right? These files are very large. And they work really hard on making them smaller, but you can only make a pig so small, right? No matter how much you try to trim it and compress it, and eventually there's some mathematical like endpoint where you can't overcome like math, right? So then if you're Netflix over here and you want to deliver something over here, how do you make it easier? Which is really, how do you make it cheaper?
Put some like stuff over closer.
Oh, you put it closer, right? Yeah. You're like, oh, Amazon. I hear you have something in Denver. Big data center in Denver. We would like to put some of our content right there. Right? So there's less hops. Right? So, but from a architecture perspective, this is really a good idea. Right? Because in Denver, there's lots of Netflix users. Right? And some of us are down in Colorado Springs, right? And so we have Netflix too. And so from, if you had 4 nodes on this side and Netflix in the old-fashioned model, right, you have to do 1, 2, 3 jumps, and you have to do that 4 times. It's a lot of traffic, right? In reality, if we do trace route, there's a lot more than 2 things in the middle, right? Not only that, it's also slower because every hop is a latency issue, right? So if we can move it here at Amazon, now we do 1, 2 to get it to Amazon, right? And then 3, 4, 5, 6. And so we've halved our bandwidth, right? We can do other tricks. So then the next question comes is, why are we doing, let's talk about that old switch network. There is nothing faster than a fully connected network. If I can talk directly to your computer, right, that is the fastest things can be. Well, then we can just tinker around with this physical connection at the bottom and make it faster and faster and faster and faster. Right? And it's very simple. Right? So in the old-fashioned way, right, we have a fully connected network. You can see where this is going to go, right? This is the fastest network you can have. Why don't we do that? Yeah. Wow, expensive, right? Ironically, we can do this with wireless, but it doesn't work. We can have a fully connected network with wireless because, air is cheap, right? So, but you have to run wires here or something, some kind of physical medium, right? And so it's an exponential increase, right? You need, for our 6-node network, you need 6 wires for the first computer, right? 5 wires for the second, and so on and so forth, right? It's the sum of all of them, and it's a big number, right? So, while this is the most optimal network, it is infeasible to create, particularly with something with the internet that has whatever the connections are, billion, right? So it'd be 1 billion times 1 billion minus 1 over 2, which is a very, very large number, right? And it's not going to happen. So in order to do it, we do the statistical multiplexing of our node network that we talked about, right? And we over provision it because we want to utilize the network as much as possible. Actually, most of the goals in network optimization is network utilization, right? How do we keep the network full? And then how do we put more data in a full network? That's really the only 2 questions, other than, hey, does it still have some kind of reliability that you have to meet? in our network that we've been using, our 4-node network, right? This is client, or server, whatever, right? What are these things in the middle?
Could be a
Physical area.
Yeah, whatever. So most of the time, in the deep middle of the routers, right, right next to the client, there's switches. Right? Or an access point, which is really a switch. Right? So, now, I just keep drawing these lines. This just comes to your GPS thing. So most of these are full duplex, right? They're a communication link that you can talk to both ways, and you can do it at the same time. Almost always when we talk about it, networking, we're talking about full duplex. They haven't had half duplex in a long time, right? That's the mistake that you made on Amazon. You should have read the details. It's like, why is this router so cheap? Right? Because it came like circa 1984, right? So, these are duplex, right? Which means that it can go both ways at the same time, right? A half, if you look at diagrams, is often looks like that, which means it can go both ways, but only at one time, right? And then you have weird networks, which I believe the book says almost don't exist. And then I started thinking about GPS projects for PhDs, and then I was like, oh, it's GPS. GPS is a simplex network. Your GPS in your car does not send signals to satellites, right? It only receives them, right? These are one way, kind of like broadcast TV. So, if I drew this, right, with more clients and more routers, these are all physical connections, right? There's no physical connection from this client to this client or to that client. Now, we're going to take a glimpse into something that doesn't have wires. And this will explain why there's going to be a number of problems on tests and stuff about wireless. So we have clients and an access point, and we're communicating wirelessly. So, for various reasons that we will talk about in the future, this is a collision avoidance network. It cannot detect collisions. Wires, not miraculously, but can, right? So we think of it like this. We only connect to UCCS as wireless, right? For the guys that are on the computers. But this is a broadcast medium. It is broadcasting everywhere. So in reality, there is in fact a connection for these three here, but maybe this one's out of range, right? But this one has its own connection. And so on and so forth. They're all interconnected. This is a mesh network. The problem is, if I want to talk, what happens if somebody talks at the same time?
It slows it down.
Broadcast louder.
Yeah. What happens if you're trying to get a text message out in the eclipse? Right? Because we're not just talking about Wi-Fi here, we're talking about cellular, anything that's wireless, right? So I want to get a text message out with my cool, and I got a really good picture of the eclipse, by the way. I want to get that text message out. Nothing goes out, right? Got 3 bars, 4 bars, well, it doesn't matter. Because that bar is literally measuring like how strong the signal is here. It's not saying how good the network is. It's just saying how strong the signal is, right? Everybody's trying to communicate at the same time, and so I am stepping on you, and you are stepping on him, and blah, 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 right? And the more people that we stick in here, the more people are stepping on each other. So this is essentially a telephone network where we're all connected at the same time, party line style, So,
Yeah, so I was thinking they limit wireless to 2.15 gigahertz. Wouldn't it be wise to just remove that limitation? Because it slows down everyone's wireless when they're looking at it.
well, yeah, I mean, there's some arguments on that. It also uses 5 gigahertz, right? And some of the cell phone networks are like 900 megahertz and all sorts of stuff. But the deal is like, you know, us as a people, I'll give you the logic behind it, not defending it one way or the other. But we've all decided we're going to have this part of the network to do this, and this part of the network to do this, and this part over here to do TV, and right. And so, you know, there's only so much physical, you know, bandwidth that we have, or wavelengths that we have. Right, the spectrum is finite. Physics is messing with you there, right? So. That's why we're going to talk a whole lot about wireless.
Can we use the TDMA detection?
Huh?
The time division multiple access?
Correct.
And the CSMA and
Yes.
wireless?
We'll go through all that and actually how to architect that and how it's architected. So in order to actually study this, we need a little bit of what happens on those client sides. We have to be able to, if we're going to study it, not just in a book, but we're actually going to experiment and look at things, right, and implement it ourselves so that we feel comfortable with it. We need to actually understand how to do sockets, and not everybody has done sockets, and if you have, not everybody's done them in C, right? So or C++. So we're going to, all the stuff that we do in the class will be a Linux socket, right? So you'll turn that in. But in, I think it was around '83, Berkeley Unix came up with, hey, everybody in the world's using all these crazy methods to communicate. Let's come up with a standard socket. And since we're Berkeley and we own the de facto Unix distribution, we will do it, right? And so they came up with Berkeley sockets, which was later like adopted by everybody. So even if you're programming in Windows, the call might be slightly different, right? So like the naming convention of the function would be a little bit different, but the call is still the same, right? It's basically doing the same thing. So the idea is not everybody in the world is interested in messing around in here like you guys are. Right? Most of the guys want to write apps and be rich. Right? So I'm going to write my killer app, right? It's going to talk to a server. I would like very much for this to seem like I don't understand this at all, which almost nobody understands this at all. Right? So I would like very much to only understand some IT-ish like architecture down there. Like I need to understand like IP addressing, kinda, not even really, but maybe DNS names, right? And so I would like to communicate from this, and we're gonna actually call this a client server this time, right? And communicate back to that thing. So the idea is, how do we use this down here without understanding it, right? And this is the problem that Berkeley solved. And the solution they called sockets, right? We're going to create a socket that communicates with another socket, and pretty much everything underneath we're not going to pay attention to, right? Which we'll get to layering, which we will hopefully get before the class is over, but I don't know about that. What we want to do is have a communication scheme for this thing, right? And so if anybody's ever done anything like this, or done any like wire sniffing, right? There is the client, the server, and we do a time diagram. So this is time, right? So we need to, if we're gonna, what are the things that we need to do up here? We're gonna talk to a server. because I have a killer app and it's gonna make me millions of dollars. What do we need?
Yes, and
No, we don't care about protocols because we're app developers and we don't care.
connect to it.
We gotta connect.
Yeah.
Right? We're not gonna say how we do that because we don't know. Right? We're just gonna connect. Right? Connect.
Magic here.
Yes. Then what are we gonna do?
Get a response.
Send data.
Send data, right? Which hopefully is money. And then what is what do we do next?
Receive.
Close.
Yeah. So the server sends data back, which is your virtual object that you just paid real money for, and I created in 15 minutes. Killer app. And then we close, right? And rinse and repeat. Right, that's the basic communication protocol. Right, but if we want to do it, unfortunately, Berkeley couldn't find a way to say, connect and do this, right, and close and do this. Though there's some pretty good stuff in Python, right, that does a lot of this management stuff for you. But in Connect, we really need to do a couple things for that actually to work. So, the client's going to send a message to the server, and the server needs to respond. So in order to do that, the server has to be kind of waiting for the question, right? So you write your server, and it waits to listen for a connection, right? From the server's perspective, you call, hey, I want to create a socket. And this literally called socket. This says, hey, I'm not doing any network connections yet, but I'm thinking about it. And then from a server's perspective, you're going to always listen at the same place because you don't know where the clients are coming from. So you have to assume the server knows where it is and knows where to listen because the clients don't. They're going to change all over. They're going to be mobile, right? Even on your mobile phone right now, if you're connected to UCCS network, right, you can actually start a connection and wipe it out and go to cellular, right? So the clients change dynamically. Servers are usually in the same spot, right? So you're going to call a function called, we should do this over here where it's in front of the camera because the online guys are already hating me.
Are you gonna upload those videos somewhere?
Yeah, I think it will.
All right.
Until people quit coming to class and then they it's really hard to do a class. There's like one guy and we're just talking about beer. Like, oh, here's the answer to the homework assignment. Everybody else is gonna hate life. So we got to connect, right? Let's write that there, and then we're gonna send data and receive data. I need bigger space here. Receive data, and then close. All right. So the server needs to create a socket. And then the server knows where it is, right? So it needs to tell the socket, this is where I am, right? There are various ways to do that, right? Because servers may change occasionally. But you tell it where you are, right? So this is in a function called getAddressInfo. Which is your address, right?
Including the port?
Huh?
Including the port number?
Not including the port. Because the next thing we do is like, oh, this is our IP information. Then we need, if we're doing TCP or whatever, right? We need a port, right? So that's in bind. this is the port. This is IP, which we will talk about. Right? And then, what do? We listen. You want to take a guess what the function's called?
Listen.
Listen.
Yes.
And I'm going to have to move my lines because I've already wrote too big. Right? And then, so listen isn't quite exactly what you think it is. Listen says, get ready to listen. There's another function after that called accept. So when I get a connection, accept it. Now from the server's perspective, what's next?
Hang out.
Huh?
Hang out.
So this right here, by the way, I've messed my lines all up. Because I was an English major, so. This is connect.
Oh, okay.
Right? So we still need this send and this receive.
Question. So when you listen on the network, is that when it shows like the server is working when it pings it?
So we will talk about this. Most of the time, the send and receive is in a loop. But from a real like production, like not just messing around in class, right? This whole thing is in a loop, right? So socket and get adder open and bind and listen and accept. And your first receive is go to this other port, right? Because I want to be able to make more than one connection. Google would kind of suck if only one person could connect to it at one time. Right, so we need to be able to roll them, and you can roll 64,000 on one server. Right? So, this is the connect. From the server's perspective, what do we need to do next? Receive. Which is miraculously called receive, but spelled like Jason likes to spell it. And then what do? Huh? We send. Usually this, okay, I received this request, maybe I want to send something specific towards that, right? But then it's a send. And then close. You close the connection. So when you go to Google and you connect and you get your web page, once it downloads the web page, right, it closes. Except for that little script in there that keeps connecting to send you ads. Right? Now, from the client's perspective, what do we got to do?
Initiate the connection.
Well, we start out with socket, right? And then what do? Get adder info. www.google.com returns an IP address, right, that isn't ours. And then what do? So bind has to do with picking ports. Do we need a specific port?
No.
No.
It's going to be a random port.
No. So everybody knows what port 80 is, right? It's web traffic. When you connect to port 80 at google.com, did you leave port 80? No, you left some crazy random port, right? It's a crazy random port. And so all of that stuff is handled by connect. Pick me a crazy random open port and send this message. And when it sends it, you get accept reads what crazy random port it came from, and it sends it back on that crazy random port. So now the rest of it is pretty easy. What's the next thing? Send. And then?
Receive.
And then?
Close.
All seems super simple, right? You guys are going to pull your hair out coding this. So, what has to happen first? Send or receive? Oh no. Receive has to happen first. Why?
Because it has to be ready.
It has to be ready, right? So receive has to happen first. It is also a blocking call. What's a blocking call?
Nothing else will happen. while
Yeah. It doesn't go forward until it returns, right? So you call receive, program pauses, right? Until it receives. So if the program pauses and it receives and you're like, my program's not working, right? These are part of the problems. What other ones in here do you think are blocking calls?
Accept,
Accept. Why accept?
because it also needs to be ready to wait for that to connect.
Correct. And is there any other ones? No. That's pretty it. That's pretty good.
Well, what about
Now.
close part? Once it's closed, it's
So,
not accepted.
so ironically, the server or the client can close and terminate the connection at any time. It's kind of like either we're on a phone call and I decide to hang up, or you decide to hang up. It's really only one person needs to decide that, and we can just close it. The interesting thing comes is when you close a connection and don't call close. So then the server thinks that it's still talking to somebody. And so then you have to write timeouts and stuff in there, right? So this seems all super simple, right? Like, oh, I could code that in 25 lines. Except for this not, because there's all this other stuff you have to code in there, because what happens if you get a send before a receive, right? Then you have to, you have to write exceptions, or you have to write a loop, right? Normally this stuff right here is written in a loop. And remember, Google wants to talk to more than one computer, right? So this stuff right here is written in a loop. So you accept, and then you shoot them off to some other port, right? But there's nowhere that says, hey, use 802.11 Wi-Fi, right? All that stuff is totally abstracted, right? So we have our client and our server, and they want to virtually communicate with each other, right? But they don't really virtually communicate, or they don't really directly communicate to each other, right? We call socket, right? Socket calls connect, blah, 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 blah. And then there's things that happen underneath there that we don't even call. It's so abstracted that there's nothing to even actually call, right? So what happens is we have this layering, right? And each of the layers on the client side go down and the server side go up, and then when it sends a communication the other way, it switches, right? But they each virtually talk to each other as well. And they're not really talking to each other until you get down to some kind of wire or radio, right? Once you're down to physical, they're really talking to each other, right? But you don't want, if you're writing your killer app, you don't want to have to study how wires work and communications work, right? Down here. You really want to stay up here somewhere, and if you're really innovative, ooh, maybe you'll use this, right? But you definitely not want to go to the bottom, right? So, but obviously if we're designing networks, somebody has to do that work. So they all virtually communicate each other. This is where the concept of layers. So who has heard the OSI 7-layer model? Who understands that the OSI 7-layer model is not used anything anywhere, ever? It was conceptual and then there's no actual implementation of it, right? So why is that?
They use the TCP/IP model instead?
So yeah, The first reason was, the first reason was TCP/IP came out before the OSI 7-layer model did. And people want to make money, and in particular in business, we all took the same class together, and we even chatted after lunch on how cool it would be, and then it all dawned to us at the same time that, hey, we could go make money, right? So then we all try to beat each other in the market, right? And the first guy market with an acceptable solution, not the perfect one, an acceptable one, wins, and TCP/IP was that acceptable solution, right? And so TCP/IP doesn't follow the 7-layer model, right? But we'll talk about it because we have to, and then we'll talk about a real model, like the internet model. In the OSI model,
Please don't throw sausage pizza.
huh?
Said please don't throw sausage pizza away. I use that to number.
That's right. So we start out with, at the top is the application layer, which is a real layer even in the real world, right? What are application layers? Example of? HTTP, right? SSL, that's all the things that we were talking about earlier, right? And then underneath the application model is the presentation layer, and then the session layer, and then we get down to transport, which is a real layer, right? And transport does what? What is transport responsible for?
The port
End to
numbers.
end.
Huh?
End to end.
End-to-end communications, exactly right. So the transport layer is also responsible for deciding on whether it's reliable or unreliable end-to-end, right? But it is that end-to-end communication, right? In transport layers, we talk about frame. I don't really, from an application developer's perspective, care how many times you chunk this up to send it over the network efficiently, right? I really care if I'm Google that my results page arrived to you intact, right? That's the transport layer. Underneath that is the network layer. What does network layer do?
Networking.
Is packets, right? Transport layer is frames, and the network layer is packets. These are all the little pieces that we cut it up. So our network is most efficient if we use a packet length of 6,400 bits, right? And then we come up with another network underneath that, a different network, and we say, oh, the network layer is now more efficient if we use 1 megabits, right? But it really doesn't matter to the transport layer because it's really just dividing it up. Where do you put the divisions, right, before you send it off? The network layer is also responsible for this thing in the middle that we never change. And what is that? We try to change it. We talk about changing it for like 2 decades. And it's still not that changed. It's just IP. IP. It's the narrow waist of the internet. Everything runs on IP, right? It's really easy to change. The further you get away from IP down or above, easier it is to change. This app stuff at the top, right? You and I could create something today. Put it on the internet. Whoa, new protocol, right? Not going to be easy to change this, right? A lot of people, a lot of very large influential companies, including Intel, want to change this, and they can't, right? Because you're actually asking to change the whole internet, right? So, this is transport, right? Addressing, and then we have physical addressing stuff below it, right? But we'll talk about the layers next time, and because all this other stuff was just a foundation network of going in, this you need to know, and we'll talk about that as we go.